Okay, so let's get started with our first amplifier or first amplification stage using the MOS transistors. We're going to start with common source stage, similar to the way that we did with common emitter stage in the BJT transistors. So the terminology is pretty much the same. We follow the same rule for naming these stages. So when we say common source stage, it means that source is the only terminal that's not connected to neither input nor output. Okay, so the input is connected to the gate, output is taken from the drain. Let's say I have connected this input to some signal source and some battery for biasing. So there's a VB here, and let's say this is my VIN or V signal. Okay, now because I want to calculate the gain, let's say that I've already done the DC analysis, I've already biased these transistors, I've already had those discussions up to now. I just want to calculate the gain of this stage, right? So because it's gain, I have to go to the small signal volt, right? So I have to draw the small signal model. So the small signal model, we have discussed it last week. It's very similar to what we did with the BJT, except that we don't have an R pi here simply because the gate is connected to some sort of a capacitance, right? So I'm going to call here V1, or I can call it VGS. I'm going to have a GM VGS, and for now, we don't have any channel length modulation, so forget about the R0, right? But then if I had an R0, it would have been between drain and source, which source is ground, so R0 would have been here, so it would have been in parallel with this RD. So it wouldn't actually make things a lot more complicated, but then for now, let's just keep it as simple as it gets, right? Now, what would be V out? If this is the definition of V out, I know that V out is equal to RD times some I out, right? Let's say this is I out. And since I out is negative GM V1, because it's in the opposite direction, I can write V out to be equal to negative GM V1 times RT. And looking at the circuit, I can see that Vin is basically, because it's small signal, this bias voltage is actually shorted, so I only have Vin in the AC model. So this is my Vin, and you can see that Vin is from this point to ground. So is V1. V1 is also from this point to this point, which is ground. So V1 and Vin are the same thing. So I can write this as negative GM RD Vin. And based on that, the voltage gain of my circuit is going to be basically this equation, negative GM RD, right? Very similar to the BJT stuff that we did before. So it's basically in common emitter, we had negative GM RC. Here we have negative GM RD, simply because over there I had collector, here I have drain, okay? So this is the similarities that make things a lot more simpler, okay? Now, what is GM? Well, for the GM, I could have any of these expressions, right? And all of them, it's not like that basically they're different expressions. They're pretty much the same expression that I've written them differently. So the expression that we learned we have from GM for GM, this is the expression that we originally found. But you can see that if I write ID in saturation, which is equal to 1 over 2 mu n Cox W over L VGS minus VTH squared, then you can see that if I multiply this expression by 2, so 2ID, and then divide it by 1 VGS minus VTH so that the square sign goes away. So 2ID divided by VGS minus VTH is going to give you this expression, right? So this is basically 2 times that expression divided by VGS minus VTH. That's why I can write GM equal to 2ID over VGS minus VTH. Similarly, like for this expression, if you just basically replace this ID here with that expression, and then basically simplify the equation, you're going to get to this expression. Okay, so these are basically the same expressions. Basically, why do we have different expressions here? Because for BJT, remember we had just IC over VT, right? Well, the reason is that sometimes you have the current and you have the W over L and mu n and Cox, so you use this expression. Sometimes you don't have the current, you just have the gate VGS, the gate source voltage, right? Well, you use this expression. Sometimes you have ID and VGS minus VTH, you don't have these guys, right? So depending on what you have, what is given to you in the question, you can use any of these kind of parameters or any of these equations to actually get to the GM that you want. Okay. Now for this case, I'm going to use the first equation. So this one, right? I'm going to replace this GM expression into this gain. So my gain is going to look like this. So negative root square of 2 mu and Cox W over L times ID, and then there's an RD outside of the root square sign. Okay. Now there are a couple of questions that we need to answer. Number one, so this is the question number two perhaps. Number one is basically, how do I increase the gain? So how to increase the gain or the AV. Okay, for doing that, I have to actually look at the gain expression. Looking at this expression, I can see that mu n and Cox are device parameters. I have no control on them. But W over L, these are the size of my transistor. This is the width and length of my transistor. So I can actually design the transistor to be bigger, like wider or well shorter, so that I can get more gain, right? Same with ID. That's a biasing current of my DC current of my transistor. I can actually set it to have a higher value, therefore I can have a higher gain. And also RD. So it's a resistor up here, so I can actually set it to any value that they like, and I can get higher gain, right? So let's actually write the options that we have. So option number one is W over L should be increased. Option number two is ID should be increased. And option number three is RD should be increased. Now, out of these three options, I can appreciate that if I multiply W over L by 2 or multiply ID by 2, my gain is going to be only multiplied by root 2, right? So it's not going to be as effective as if I multiply RD by 2, because, well, that has a linear relationship with my gain. So it's going to be basically give me 2 AV, right? But that's actually the less important reason that I like RD compared to these two other options. The more important reason is that, well, if I increase ID, yes, I do get more gain, but then at what cost? The question is, at what cost do I get this more gain? Because there's no free lunch in this world. The cost that I pay for increasing the gain here is power consumption. Because if you remember, the power of my circuit is always VDD times the DC current that is drawn from the VDD. In here, I just have one branch coming out of VDD, so it's going to be VDD times ID, right? So the moment I start increasing ID, I'm linearly increasing my power. So every time I multiply my power consumption by 2, I'm only getting a basically gain increase by a factor of a root 2. So it's not a good bargain. It's not really something that I like. Still, if I don't have the option to change this resistor or the size of the transistor, I might actually go to this option, but it's not the most kind of like attractive option, at least, right? Same thing with W over L. It might sound or might seem innocent because it's the size of the transistor, so like it's not going to have anything to do with the power. But then if you look more carefully, if you look at this equation, you're going to see that the moment I start to increase W over L, I am increasing my ID, again, linearly, right? So again, if I basically make my transistor twice wider or twice shorter, yes, I get root 2 times more gain, but then, well, I'm going to be spending twice as much power, right? So it's kind of like I'm paying twice as much money, right? Power is always money in IC design. Always think about it that way, right? And RD, the last option that we have, right? If you look at that, you'll see that if I increase the resistor, it has nothing to do with the current. So basically, I get twice as much gain, so even better improvement, at almost no cost, at least from the power perspective, zero cost, right? Is there literally no cost? Well, that cannot ever be true, right? So there's always some cost that we're paying. So the first thing that we're paying is area, right? So like if I have a 1 kilo ohm resistance and I make it 2 kilo ohm, well, it's going to be basically twice as much area, right? But is it that important? Well, definitely an order of magnitude less important, let's say, a lot less important, significantly less important than power consumption. So I am flexible, a lot more flexible with the area compared to power. as long as area increase is reasonable, right? So like, yeah, if I have a 1 kilo ohm and I make it 1 mega ohm, then yeah, I'm going to be taking a lot of area on my silicon chip. So that's not really something that I like. But going from 1 kilo ohm to 2 or to 10, that's fine, right? Because your amplifier at the end of the day, think about it this way. Your chip might have actually thousands of amplifiers, and each of those amplifiers is going to be basically taking not even 0.1% of your chip area. Let's say it's basically 0.001% of your entire chip area. So you can imagine that if you multiply that area by, I don't know, like increase the area by 50%, it's not going to be the end of the world, right? So that's why I like RD. Now, there's another thing that I have to actually consider when I'm increasing RD, and I've actually hinted that in the previous slides, that, well, for this transistor to be working like an amplifier, and for me to be able to actually even draw the small signal model, first I have to make sure that my transistor is working in the saturation region, right? What's the condition for saturation? So to be in SAT, I know that I have to have VDS greater than, greater than VGS minus VTH. Again, I've mentioned this a few times, but we call this the overdrive voltage. Sometimes we just show it with OD, right? Now, VDS is VD minus VS. VDS is equal to VD minus VS, should be greater than VGS, which is VG minus VS minus VTH. So VS cancel out. In this case, VS was 0, so I didn't even have to write this equation, but even if it's not 0, you can see that it cancels out. So basically, it tells you that your VD should be greater than VG minus VTH. Okay. Now, assuming that my gate is connected to DC voltage, by the way, all of these stuff, checking the transistor being in saturation, is a DC kind of a discussion, right? So the DC voltage at the gate is the bias voltage. So that's constant, and threshold is constant. So all I have to make sure is that my VD is greater than this constant value. So now, what is my VD? Let me draw a line. So VD is equal to VDD minus RD IT. Okay, so now I can see the problem. This is the important expression. VDD is constant, but if I increase RD or ID, it means that I'm actually decreasing VD. If I'm decreasing VD based on this equation, I can see that I'm getting closer and closer to this constant value that is setting the threshold, or setting the condition for being in saturation. Okay, so this means that if RD goes up or ID goes up, so this is another reason that I don't like to increase ID, other than the basically the power limitation, the power increase that it causes, and the fact that it only gives me a √2 increase in the gain. It also might actually cause me to go to triode, right? But if I increase RD as well, I can see that either RD or ID, if they're increased, I'm getting closer to triode. Okay, so this is the answer to the second question. So what is stopping us from increasing the gain? Well, going to saturation is really the thing that is stopping you, right? So as long as you can make sure that you're not going to saturation, then you can actually increase RD with almost no cost, with just a little bit of an area cost, you can actually get more gain, okay? So all of these discussions are very similar to the kind of discussions that we had with BJTs and the trade-offs, right? You can see that, I'm hoping that you can see the resemblance, the similarities between the two, that, yeah, RD is actually setting my gain, but it's also the parameter that is also, if it is too large, so because it's setting my gain, I want it to be large, but at the same time, if it's too large, it might actually take my transistor out of the operation region that I like it to be, which is saturation. Okay, so let's solve an example. Here, the question is asking us to calculate the small signal gain, voltage gain of the common source stage, shown below if ID is equal to 1 milliamp. So the bias current is actually given to us, so we know that this Vin is connected to not only just a signal source, let's say Vin, but also some sort of a DC source or battery. Let's call that V bias, right? Somehow that V bias is set. We don't care how much the voltage this bias voltage is at the moment, but somehow it resulted in 1 milliamp flowing through this transistor, right? And then mu and Cox is given, so the device parameters, physical parameters are given. The threshold voltage is 0.5 volts, the lambda is 0, meaning that there's no channel length modulation, so no CLM, or in other words, the R0 is actually infinity. And the question is asking us to calculate the gain and also to verify that the M1 operates in saturation. The transistor is in saturation. Okay. By the way, the W over L is also given here. Okay. Now, what is the gain? I know that from previous slide. By the way, I've written these GM expressions from previous slide again here just to speed up the process. But if you wonder what is this VOV, it's basically the overdrive voltage. So it's basically this VGS minus VTH. Okay. So AV, I know that it is equal to the V out over V in, which is negative GM RT. Okay. Now I have the value of the RT. How about GM? Well, let's take a look at these expressions and see which one of them is actually I can use, right? I can see that I have ID, I can use W, I have W over L from here, I have mu and Cox, so I can use this expression. But then how about these two? Well, the fact that I don't have VGS minus VTH, simply because I don't know what is the VG yet, the DC voltage at the gate. I don't know that, so I cannot, at least I can calculate it, but it's not given. How can I calculate it? Well, I know that the current of a MOSFET in saturation is 1 over 2 mu n Cox W over L times VGS minus VTH squared, right? So since I have ID and I have these stuff, then I can calculate VGS minus VTH. I have VTH, so I can calculate VGS, right? So I can calculate it, but then it's an extra step in my solution, right? So I can just go with this guy and say that, well, I have everything because these other two, they have this VGS minus VTH here and also here. So because of that, I'm going to go with the third equation. So I'm going to say that GM is equal to this, which is equal to, so 2 times 100 microamp per volt squared. That's the unit. I know it's weird, but it is the unit because, well, that's how, like, that's the unit that makes sure that the GM unit, which should be in amp per volt, is it works out, right? So the W over L is 10 over 0.18. It's unitless because we have the length over length, so their units cancel out. And we have basically RD, which is, ID, that is 1 milliamp, so 10 to the negative 3, all under the root square. So if I calculate this, plug in the numbers, and you're going to get 3.33 milliamps per volt. I encourage all of you guys to do this simply because I want you to do a few of these calculations and make sure that you get the right answer and you don't make that kind of mistake in the exam. Now, based on this, I can say that my voltage gain is going to be this negative 3.33 milliamp per volt times RD, which is 1 kilo. Kilo and milli kind of cancel out, and then I get the gain of negative 3.33 volts over volts. Okay, so that's my voltage gain, and I'm pretty much done with the first part of the question. Now for the second part, I know that for M1 to be in saturation, I need to make sure that VDS is greater than VGS minus VTH. Okay, so what is VDS? VDS is equal to VD minus VS, VS being ground, so that's 0. So it's going to be just VD, which is equal to VDD minus RD ID. VDD is 1.8, RD is 1 kilo ohm, ID is 1 milliamp, so 1 volts is going to be RDID. So this is going to be really 0.8 volts. Great. Now, how about VGS? Well, first I have to actually calculate the VGS. So I know that based on this equation, I know that 1 milliamp is going to be equal to 1 over 2, 100 microampere per volt squared, times 10 over 0.18. By the way, W over L, a lot of times you might wonder why don't we just show one number here and we show both numbers and the ratio. It's just basically a standard way of showing W over L so that not only we know the ratio, we know the actual value of W and actual value of L. Okay, it's nothing more than that. I know it looks new and strange, but this is the reason that we show W over L in this form. And then this is going to be equal to VGS minus VTH squared. Therefore, if you do the math, you're going to get VGS minus VTH squared equal to 0.36. Therefore, VGS minus VTH is equal to 0.6. Okay, and since the VGS minus VTH 0.6 and VDS is actually 0.8, then I know that this condition holds and we are indeed in saturation.